The division lemma states that given any integer a and a non-zero integer b, there exists unique integers q and r such that a can be written as q times b plus r, where r is non-negative and less than the magnitude of b. So let's look at some examples. Let's suppose a is 5 and b is 2. Well, there's a unique pair of integers q and r, so that we can write 5 as q times b plus r. We have to choose q equal to 2, we've no other choice, and then r will equal 1. So notice of course that r is non-negative, 1 is non-negative, and 1 is less than the magnitude of b, 1 is less than 2. Let's take the case where a is minus 10 and b is minus 3. Well then, in order to satisfy the conditions of the lemma, we have to choose q equal to 4. So that means we get a value of r which is 2. And this is unique. There's no other pair that satisfy the conditions. You can see that 2 is a non-negative number and it's less than the magnitude of minus 3. Here are some more examples. I just want to mention that if b is 0, then we get into trouble. Okay, so I've taken the example where a is 5 and b is 0. So if we try to write 5 as qb plus r, we end up getting that r equals 5. But remember, r has to be less than the magnitude of b. And if b is 0, well, the magnitude of 0 is 0, and r is non-negative. R cannot be less than 0. So for that reason, we cannot have that b is equal to 0. To prove the lemma, we consider the set a minus xb, where x is an integer, and a minus xb is a non-negative integer. Okay, so we're dealing with all non-negative integers of the form a minus xb. First, we will show that this set is non-empty for all integers a and non-zero integers b. So we have to consider a few cases. Let's first take the case where a is non-negative. So can we find an integer in this set? Well, if a is non-negative, then it doesn't matter what b is. If we choose x to be 0, which we can do, we can choose x to be any integer, then we get the integer a minus xb, which is just a, which is, as we stated from the start, is greater than or equal to 0. So in the case where a is greater than or equal to 0, then for all b, we've found an element of the set. Now the other possibility for a is that a is less than 0, but now we have to consider two cases separately. We have to consider the case where b is negative and where b is positive. So let's start with the case where b is negative. So we want to get an integer of the form a minus xb. We can choose x to be anything. Now if we choose x equals minus a, we'll get a times 1 plus b. A is negative. Now since b is negative, it's a negative integer, it's minus 1, minus 2 or minus 3, etc. If we add 1 onto it, we get a non-negative integer, 0 or minus 1 or minus 2, etc. So when you multiply these together, a by 1 plus b, we do indeed get something that's non-negative. So when a is negative and b is negative, we do find elements in this set. So now let's look at the other case for when a is less than 0, that is when b is greater than 0. So if we let x equal a, we find that we get a times 1 minus b. Now a is negative, b is positive integers, plus 1, plus 2, plus 3, etc. So 1 minus b would be 0 minus 1 minus 2, etc. So 1 minus b is a non-positive integer. So when we multiply a by 1 minus b, we do indeed get something greater than or equal to 0. So we found that for when a is less than 0 and b is greater than 0, we do get elements in our set. Now we've covered all the cases, so for all a, b and c, with b not 0, the set a minus xb with x and z and a minus xb non-negative is a non-empty set. And it's a non-empty set of non-negative integers. So we can apply the well-ordering principle. So for a given a, b and z, with b not 0, we can find an element q and z, a number q and z, such that a minus qb is the least element in this set for the given a and b. So basically we have found integers q and r is just a minus qb. Okay, so r comes from our set, so r is non-negative. So we need to show that r is less than the magnitude of b. We need to consider two cases for b. So b can be positive or negative. So let's take the case where b is positive, strictly positive. B is not 0. So if b is greater than 0, its magnitude is just equal to itself. So we want to show that r is greater than or equal to b. Well, we're going to suppose that r is greater than or equal to b and get a contradiction. Okay, so we put r greater than or equal to b, rewrite it, and notice that we get an integer of the form a minus xb. X in this case is just q plus 1, which of course is an integer, since q is an integer. So this thing belongs to our set. However, we can show that this new element of the set that we've gotten is actually less than a minus qb, and a minus qb is supposed to be the least element in the set for our given integers a and b. So to see that, if we just expand this out, we see that a minus q plus 1 times b is just a minus qb minus b. So we're taking a minus qb, which is the least element in our set for the given a and b, and we're subtracting something positive from it. So we end up getting a number that's smaller. It belongs to the set because it's non-negative, it's greater than or equal to 0, but it's smaller than our least element, so that's our contradiction. So for the case where b is positive, we show that r cannot be greater than or equal to the magnitude of b, so r must be less than the magnitude of b. Now let's consider the other case. That is the case when b is negative. If b is negative, its magnitude is just minus b. So again, we do a proof by contradiction. Suppose that r is greater than or equal to the magnitude of b. In other words, a minus qb is greater than or equal to minus b. So we rearrange this inequality and notice that we get an integer of the form a minus x times b, where x is the integer q minus 1, and it's non-negative, so it belongs to our set. However, if we look at this here, a minus qb plus b, we see that it's actually less than a minus qb, because we're taking a minus qb and adding something which is negative onto it, so we get something smaller than a minus qb. And that's our contradiction, because a minus qb is the least element in our set for the given a and b. So we've shown that r is less than the magnitude of b, not just for b less than 0, but also for b greater than 0. So r is less than the magnitude of b for all b non-zero b in z. So we've shown that for any integers a and b, where b is non-zero, we can write a as qb plus r, where r is non-negative and less than the magnitude of b. Next, we need to show that q and r are unique. So to do that, we assume that we have another pair, q prime and r prime in z, such that a is equal to q prime b plus r prime, where r prime is non-negative and r prime is less than the magnitude of b. So let's look at these two equations and subtract them. So subtracting the left hand sides, we get a minus a is 0, and subtract the other sides and we get q minus q prime b plus r minus r prime equals 0. Now let's look at these two inequalities over here, and we will learn something about r and r prime. So I've taken the second inequality and multiplied it by -1 and written it under the first inequality. Now I'm going to add these two inequalities together. Notice that onto 0 I will add minus the magnitude of b to get minus the magnitude of b, and onto r we add minus r prime. We get a strict inequality here, a strict less than, because we're adding to 0 minus the magnitude of b, but we're adding to r on the other side something that's greater than minus the magnitude of b. Minus r prime is greater than it, so this less than or equals becomes strictly less than. And a similar thing happens for the rest of it. So we found that the distance between r and r prime is strictly less than the magnitude of b. So this result makes sense because both r and r prime are non-negative and they're less than the magnitude of b. So obviously the distance between them, you know, is going to be non-negative, but it's also going to be less than the magnitude of b. So we use that fact here by taking magnitudes of this equation. So first of all, I'll just rewrite this. And if we take magnitude of both sides, well, the distance between r and r prime we've just shown is less than the magnitude of b. Now b is not 0, so we can divide both sides by the magnitude of b and get that the magnitude of q minus q prime is less than 1. Q and q prime are both integers, of course, so if the distance between them is less than 1, it means the distance between them must be 0. So if the distance between them is 0, then q minus q prime is 0, so q is equal to q prime. So q is not unique. And if we plug it back into our equation up here, well, we end up getting that r is not unique either, so r is equal to r prime.